Let me start. Yeah, so welcome for our second talk today. So the speaker is Chenxi Wu, and he will talk about any Perron number can be a stretch factor of an end-periodic surface map. So please.
Okay. Firstly, thank you so much for giving me a chance to speak. And also, I apologize that I'm using the cell phone, so the screen aspect ratio may look a little bit weird. But I don't have Wi-Fi in my room at the moment, so I have to use cell phone. And this is a collaboration with Marissa Lavin, who is also in UW-Madison, and also Paige Hillen, who is a postdoc at UW-Madison. I think she's maybe looking for the next position soon. So this is something, a paper that we posted last month. So it's on arXiv, and this is the arXiv link. The idea is that we are considering a kind of slightly more generalized, not necessarily a generalized family, but a different family of mapping class group. So a different object as the usual mapping class groups. So we know that we have the usual mapping class groups. We can consider a surface of finite type, and then consider the mapping classes, homotopy classes of self maps from the surface to itself. But if we want to consider infinite type surfaces, we have the corresponding concept of a proper homotopy equivalence and also proper mapping classes. But in general, studying proper mapping classes are going to be difficult. So this is maybe the Endperiodic mapping classes is just a much smaller family among all the proper mapping classes that one can build a more or less complete theory. So what's the definition? So the definition goes as follows. So if we consider a surface S with possibly infinite genus, so infinite topological type, and then it has finitely many ends that are accumulated by, it can be accumulated by genus or accumulated by punctures. So we can also consider surfaces with punctures. And then we require that among each of these ends, there will be a neighbor. So here the definition of an n is basically, let's consider the surface without puncture. Then it's just a surface. In that case, then the n is just the complement of the. We can consider the complements of a compact part of the surface, and then just make the compact part larger and larger. The resulting things, the complements will just become the ends. So in particular, for every n, we can consider a neighborhood. And then we say that we have a homotopy equivalence or a homomorphism from a surface without puncture but infinite genus to itself. We say that this is a map which is an Endperiodic surface map if it satisfies this property, which is that we can consider a neighborhood of each n, and then if we raise f to some power, then that neighborhood will get sent to either a smaller neighborhood or a larger neighborhood. So either a strictly smaller neighborhood or strictly larger neighborhood. So that's the idea of being Endperiodic. So basically, the behavior around the ends are going to be regular. Everything's are just moving away or moving towards the compact part. But the behavior inside the compact part, it could be however we want. So as an example, if we start with a closed surface, we can consider a regular cover with that transformation group Z. So it's a Z-fold cover. So for that, as tilde, we think about it like a surface with infinite many genus, and then arranged horizontally. So it has two ends corresponding to going to infinity in two different directions. And now we have the deck transformation. So we can just shift everything to the right. So we call that H. And if we have another homomorphism from this infinite genus surface to itself, which is what we call compactly supported. Here, by homomorphism being compactly supported, we mean that there's a compact region where the homomorphism is not identity. So outside this compact region, it's just identity map. So if G is such a map, then we can compose the deck transformation and G in either direction. So H composed with G or G composed with H. Both of these are going to be Endperiodic. So this is maybe the simplest example of an Endperiodic surface map. Of course, this H itself is Endperiodic as well, but it's like topologically not interesting. So if we compose it with something compactly supported, then topologically it becomes interesting. So as I said earlier, so what's the motivation for studying these kind of mapping classes instead of, so the idea is that the original, like the mapping classes over finite genus surfaces or closed surfaces that have there's already a fairly complete theory. So well, not really complete theory, like extensive theory. The idea is that we want to push those kind of theory to infinite genus surfaces or infinite type surfaces. But in general, it's difficult to do it for arbitrary mapping class homomorphisms from infinite type surface to itself. In particular, the number of elements in that group is going to be even like uncountable. So it's something that's difficult to manage. But if we consider Endperiodic ones, they are in some sense elements, mapping classes on infinite type surfaces that can be determined completely by finite amount of data. So you can, for example, in this particular example that I wrote in the slide, if we know the genus of the surface S, we know this cover, and then G is compactly supported. So basically, we just need to know what happens for G inside a compact region. So the genus of S and also the behavior in that compact support, the behavior of G inside the compact region, both of these are finite amount of data. So it's possible to write this down using this kind of simpler information. And also, there's a more or less analogous theory for Endperiodic mapping classes compared to the original mapping classes, compared to the mapping classes for finite genus surfaces. So that's why we care about it. Well, that's one reason why we care about it. So another reason is, of course, that this is not just like an object that we just come up with at random. It also arises naturally in other areas of mathematics. So in particular, when we are studying depth one foliations in free manifolds. So here we mean a foliation of a free manifold by two-dimensional leaves, and there are some closed leaves, and also some other leaves which accumulates to the closed leaves. So if we are in that kind of situation, we can think about the leaves that accumulates to closed leaves. Those are basically, in general, going to be surfaces with potentially infinite topological type. So either infinite genus or infinite many punctures. And those leaves, because they get really close to the, well, if we consider, say, the monodromy of that foliation, then because those leaves, they become really close to the closed leaves, you can think about those as like when we are traveling towards infinity, it's more or less just we are going to have like many copies of surface, like many pieces in the surface, which locally looks like, which topologically just look like the closed leaf. And then the behavior there is going to be fairly regular because that's near the a small neighborhood of the closed leaf where we completely understand everything. So this is the motivation for why Endperiodic surface maps arises naturally from depth one foliations of free manifolds. Another more concrete way of thinking about this goes as follows. So if we have an Endperiodic map, for example, Endperiodic surface map, for example, the one that is like H composed of G in this example, so we can consider just the mapping class of this particular surface map from S tilde to S tilde. And if we just look at the mapping class, so, the mapping torus, so just multiply with I and then glue one side with another using this H composed with G, if we look at this free manifold carefully, we see that this is actually a free manifold with cylindrical ends. So the ends are going to be basically the ends are of the form of S times an interval. So that's the topology of the end. And each of the leaves of this, well, once we have a mapping torus, we can consider like the different horizontal copies of the surface. Those are two-dimensional leaves. Those foliates the mapping torus by two-dimensional leaves. But each of these leaves, they are going to accumulate towards these cylindrical ends as we travels towards infinity in either direction. And now once we, in this particular example, we have literally just two cylindrical ends. So one is S times the interval from say 1 go to infinity. The other one is S times another interval from 1 to infinity. So with these two cylindrical ends, we can just literally glue in a copy of S at infinity, and then just put these two copies of S's together. So now we get a closed free manifold. And this, the original foliation on the mapping torus, together with this single copy of S at infinity, that's actually a depth 1 foliation. So this is a more concrete example of getting a depth 1 foliation in the surface with, so that the non-compact leaves correspond to, so that the dynamics in non-compact, monodromy non-compact leaves are Endperiodic surface maps. Yeah, so of course, that's just like a single example. If we want to do the more general construction, we need to consider more cases. For example, potentially the ends are going to have different topology. In that case, we need to do doubling. And then also we need to impose further constraints on the Endperiodic surface map so that the resulting free manifolds are in some sense good. So if we want to see the details of this construction between the this relationship between Endperiodic mapping classes and depth 1 foliations, there's the classical paper by Finlay, I think dating back to the 1980s, but there's also a more recent work by Landry-Minsky-Tyler, where they essentially just show that, yeah, we have the complete correspondence between Endperiodic mapping classes with some further conditions and this depth 1 foliation, monodromies of depth 1 foliations. So yeah, they have a more detailed argument. So this is the motivation. So it's not just an object that's easy to study when we want to understand like mapping class groups of infinite type surfaces. Well, it's not just a good small family inside the mapping classes of infinite type surfaces that are easy to study. It also arises naturally from the study of topology and geometry of free manifolds. Okay, so earlier I mentioned that the Endperiodic mapping classes has a theory like that's kind of analogous to the classical mapping classes over finite surfaces. And in particular, in the classical mapping classes, in other words, mapping classes over finite surfaces, there's what's called the Nielsen-Thurston classification. So if we have a homotopy equivalence from a surface to itself, where from a closed surface to itself, and of course we need to exclude some like really trivial cases. So yeah, hyperbolic surface to itself. So in that case, we have three possibilities: either the mapping class is of finite order, or it's someone is multiple is going to preserve a collection of disjoint non-trivial loops inside the surface, or the last case is what's called the pseudo-Nassau case. So in that case, the map is going to preserve a pair of transverse singular foliations, measure foliations. So we can also think about this Nielsen-Thurston classification in another way. We can think about it as a way of like having a normal form of the mapping classes. So once we have a mapping class, we have a homotopy equivalence from the surface to itself. but the homotopy equivalence can potentially be realized by many different possible homomorphisms. And in the pseudo-Nosov case, which is basically going to be the generic case, we can realize this homomorphism geometrically by just literally write down a surface map where we have this horizontal, where we have this pair of singular measure foliations, and then the map is just stretching in one foliation and then shrinking in another foliation. And the stretching and shrinking is going to be completely uniform. So in particular, this pair of measure foliations actually gives a complex structure on the surface. Of course, it's not unique, so complex structure up to some invariance. And so this is, we can think about this as an efficient way of representing this mapping class, in the sense that if we want to calculate the topological entropy of this particular homomorphism from this Riemann surface to itself, then it's going to, the topological entropy is going to be minimized over all possible topological entropies of representatives inside these mapping classes. So in particular, in other words, if we have another homomorphism which is homotopic to a pseudo-Nosov map, here I mean by pseudo-Nosov map I mean a map that preserves this pair of singular measure foliations, then the entropy of the other homomorphism is going to be bounded from below by these pseudo-Nosov maps. So we can think about them as optimal representations in the way that it minimizes the topological entropy. And what's nice about Endperiodic mapping classes is that we can actually build something analogous to this. So that's called the Handel-Miller theory. And for a really detailed discussion, it's in this paper by Canwell, Cullen, and Fenley. It's like more than 100 pages. So it's really complicated. It's not really like difficult argument, but it's a really, it's a really long and complicated argument. So where we need to deal with many different possible issues in topology. So we are going to have, they had like a lot of discussions of all the different possibilities for Endperiodic mapping classes. The key idea of this paper is that they want to, in order to build this pseudo-Nosov map, classically the idea is that we just pick a curve and then just pick a generic closed curve and then just iterate it, do forward iteration and then do backward iteration, and they are just going to converge to the to some measure laminations, and then we can just make the lamination into foliations by collapsing complementary regions. So that's the classical idea. But here, instead of just picking some arbitrary curve, what they do, like in the Handel-Miller theory, is that they consider the boundary curves of the ends. So we have the ends which are like sending, which get sent to either some, we have neighborhoods of the ends that get sent to smaller neighborhoods or larger neighborhoods after iteration. But once we have that neighborhood, we can, so it's boundary curve of the neighborhood of the periodic ends. So we have those neighborhoods which under some iteration either get sent to something smaller or get sent to something larger. So we can just look at the boundary curves of those neighborhoods, and then just say if we have an n, which after some iteration it gets sent to some. If we have a neighborhood of an n, which after some iterations of f, it gets into a smaller neighborhood, then we just look at the boundary curve, and then we do backward iteration of f. So f to the negative, some really high power. So if we do forward iteration, it's going off to infinity, but if we do backward iteration, well, potentially it may not be able to go off to infinity. So in that case, it's just going to go wraps around the surface. And that will give us one lamination. And we can just consider ends in the other direction and go this do the same process, well, that will potentially give us another lamination. And under certain assumptions, these pairs of laminations, they are going to be transversed to one another in the compact region of in some compact subset of the surface. And outside this compact subset, everything is going to go off to infinity, either on the forward iteration or backward iteration. And basically the dynamics is happening in the compact subset where these two laminations intersect and become transverse to one another. So that's the concept of pseudo-Nosov in the case of Endperiodic mapping classes. And just like in the Nielsen-Thurston classification, another way of stating that result is that we can consider a family of curves which are disjoint and are invariant, and the complementary regions are either where the map on the complementary regions are either going to be periodic or pseudo-Nosov. So this is an equivalent way of writing down the classical Nielsen-Thurston classification for mapping classes over closed surfaces. Well, similarly, we can, like in their paper, in the really long paper, they managed to show that for like, yeah, they build this really complicated and really nice theory, which manages to show that for Endperiodic surfaces, we actually also have something completely analogous. We also have invariant curves which are disjoint from one another. In the complementary pieces, they are either going to be compact and then either going into cycles or just going off into infinity, or the complement. So if there's some complementary regions which are not compact, then either is then the map restricted to those complementary regions are either going to be shifts. So it's basically just something similar to this stack transformation H, or it's going to be pseudo-Nosov. So basically the Handel-Miller lamination is going to intersect transversely in some compact piece, and all the dynamics is going to happen there. So this is the idea. So we basically have the really analogous picture as the classical Nielsen-Thurston classification in these Endperiodic mapping classes. And in particular, if we focus on the pseudo-Nosov case, as I said earlier, so we are going to have two pairs of laminations that arises from boundary curves of neighborhoods of the ends, and they become transverse inside a compact part of the surface where the dynamics is only happening at the intersection. So this part is called the core of the pseudo-Nosov of an Endperiodic mapping class, and we can. It's also in their paper that they can actually find a finite Markov decomposition. They can decompose the core into finitely many pieces, and then the dynamics in the core is just going to be as infinite by infinite substrate of finite type. So yeah, we can just write down a graph and then write down the Markov transition graphs and consider by infinite shifts. So because it's a finite by infinite substrate of finite type, just by using classical symbolic dynamics, we can calculate the topological entropy very explicitly. So in other words, if we are in the Endperiodic pseudo-Nosov mapping case of an Endperiodic mapping class, even though the resulting surface is not compact, we can of course just add a point at infinity to do a one-point compactification, and because this resulting infinite Endperiodic map is going to be proper, so it's a continuous map on the one-point compactification. So we can write down the topological entropy of this to this continuous map from this compact matrix space to itself. And the consequence of this paper, like this long paper by Campbell, Collin, and Finley, and also the Handel-Miller construction that they built, is that in the pseudo-Nosov case, the pseudo-Nosov representative of the Endperiodic mapping class is also going to minimize this topological entropy. So starting from mapping class, we can just pick a representatives and then consider the induced continuous map of these representatives on the one-prime compactification of this infinite type surface. We can calculate the topological entropy. And in the pseudo-Nusselt case, the one that come from this Handel-Miller theory by Campbell, Cullen, and which was described in the paper by Campbell, Cullen, Fenley, that particular thing is going to minimize this topological entropy. Yeah, so in this sense, this is actually also the most efficient representation of this Endperiodic surface. Yes, some kind of a normal form. And the topological entropy can be calculated because I said earlier, like all the dynamics is really, all the entropy is really happening inside the core, and the core has a finite Markov decomposition. So the topological entropy can be calculated using that finite Markov decomposition, and in particular, it's going to be the log of some like algebraic integer. And furthermore, it's going to be a log of a weak Perron number. And lastly, so that number is called the stretch factor of this Endperiodic mapping class. And lastly, if we combine the Handel-Miller theory with the work in Landry-Minsky-Taylor, it's possible to show that we can also put this calculation of the stretch factor into the whole framework of Handel-Miller polynomial. So the idea is that if we start from that mapping class of Endperiodic surface map, and then we add in the infinite pieces to make it into a depth one foliation, we can do a small perturbation of this depth one foliation to make it into just a foliation of the free manifold over a surface, under certain actual assumptions on the mapping class. So in that case, well, once we have a free manifold, which is like a fiber over the circle where all the fibers are closed surfaces, well, that circle, the cohomology of the circle just gives us a vector inside the first term's fiber cone. And because we can do smaller and smaller perturbations, we are just finding vectors inside Thurston's fiber cone, which are getting William Thurston's fiber cone, which are getting closer and closer to the boundary. And so another way to think about Endperiodic surface maps is that we can think about those as basically representing vectors at the boundary of a fiber cone. And for Thurston's fiber cone, there's the whole theory of Handel-Miller polynomial and also varying polynomial. So we can actually also relate the Handel-Miller theory, in particular the Markov decomposition and the stretch factor for pseudo-Nusselt Endperiodic mapping classes with the Handel-Miller polynomial and the varying polynomial. So yeah, this is also some work that you can that we can see from the long paper as well as the work by Landry-Minsky-Taylor. Okay, so yeah, the point of all this is that I'm just trying to argue that it's interesting to look at this family of objects because firstly, they arise naturally, and secondly, they have an interest. There's a fairly extensive theory of them, and then we can do a lot of things that are analogous to what happens in mapping classes over finite genus surfaces. Okay, so what's our work? So the idea is, so our conclusion, our main theorem in our paper is this one. So we can define an algebraic integer to be weak Perron if it satisfies the property that any of its Galois conjugate, if we take epsilon value, the epsilon value is going to be less than or equal to lambda. So in particular, lambda is going to be a real number, positive real number. And the theorem is that the set of weak Perron numbers is exactly the same as the set of all the possible stretch factors of Handel-Miller laminations of pseudo-Nusselt Endperiodic mapping classes. And it's also exactly the same as the set of the exponents of possible minimal topological entropies of here we do not even need to assume pseudo-Nusselt, possible minimal topological entropies of all the Endperiodic mapping classes. Of course, if we restrict to pseudo-Nassau, that's also the same set. So this is our conclusion. Yeah, so compare this with the mapping classes of closed surfaces. For mapping classes over closed surfaces, we know that if it's in the reducible case, so not pseudo-Nassau, so for mapping classes in the closed surfaces, if we are in the pseudo-Nassau case, we can also write down the stretch factor. And then that stretch factor is going to be what we call the bipolar number. So it's an algebraic integer, lambda, such that all the Galois conjugates are between lambda and 1 over lambda. But the other side, the other direction is unknown. So it's unknown that whether or not any bipolar number is going to be the stretch factor of a pseudo-Nassau mapping class over a finite genus surface. So the point of our main result is that by allowing genus to go to infinity, we have the complete characterization of all the possible stretch factors, which is not really doable when genus is only finite. And there are some analogous, analogous results of this type in other setting. So there's the paper by William Thurston, I think in maybe 2014 or maybe even earlier. So the main, basically his last paper. So the idea is that the set of weak Perron numbers equals the set of stretch factors of Chenxi maps on finite metric graphs, which also equals the set of stretch factors of postclearly finite interval maps. So the entropy in dimension 1 results. And there's another paper, which is something that I did with my collaborators, and I think that was discussed by Hongming Nie like a while ago. So the set of weak Perron numbers, like also in this seminar, in the last, maybe like last month or something. So yeah, the set of weak Perron numbers equals the set of exponents of biological entropies of subhyperbolic rational maps over some non-Archimedean local field with characteristic 0. So for example, if we consider all the rational functions from Q sub p to Q sub p, so the p-adic field to itself, such that all the critical points inside the Julia set has finite forward orbit, then we consider all the possible topological entropies of such maps and take exponents of those topological entropies, then that set of numbers is also the same as the set of weak Perron numbers. So this is another analogous result. So all these theorems superficially look similar in the sense that it's the saying that the set of weak Perron numbers are basically the set of all the possible topological entropies of a certain family of dynamical systems and take exponent after taking exponential. But the proofs are very different in nature. Yeah, so basically the proofs are not analogous at all, even though the statements are analogous to one another. Okay, so maybe I can say something about the proof. So the proof is, in some sense, maybe closer to the results in Thurston's entropy in dimension 1. So the first step is that by some classical theory, a theorem by Lin, if we have a weak Perron number, then we can always write down a non-negative integer matrix where the leading eigenvalue is just lambda, or basically the spectral radius is going to be lambda. And suppose we have this, once we have write down this non-negative integer matrix, if the matrix is of size n by n, then we can construct a map as like two-dimensional map as follows. We just build n rectangles, and then we just chop them into smaller rectangles vertically. And for each of the thin vertical rectangles, we stretch horizontally and contract vertically. And then just rearrange them together into n rectangles like before. So just consider affine maps from a collection of n rectangles back to themselves, so that if we consider the Markov transition matrix corresponding to the Markov decomposition of these n rectangles, where the pieces are just n rectangles, the Markov transition matrix is just M itself. So if we consider this particular map, we are going to get something from the union of these n rectangles to these n rectangles, where the topological entropy is just going to be the log of the spectral radius of M, which is log of lambda. Okay, but like this is not going to be a surface map. On the other hand, we can just do gluings at the boundaries, like at the horizontal and vertical boundaries of these n rectangles, until this become a well-defined map, and also until it becomes continuous. So this is actually going to be a map from an infinite type translation surface to itself. So all the rectangles will be glued together into just a surface. And there will be some potentially infinite many missing points at the boundary of the surface where they get glued to many different edges. So those are like the singularities. And the singularities may also have accumulation points. Well, this is not going to be an periodic surface. The last step is the major step and also the main technical core in our argument, which is that it's possible to, so for those points which has not been glued, or as well as the accumulation points, it's possible to just blow them up to build some topologically more complicated surface, so that after the blow up process, the resulting thing becomes Endperiodic mapping class. So just to illustrate this with an example, if we consider just the matrix with literally just a single element, a 2, so it's a 1 by 1 matrix with a single element 2. So we can consider a rectangle. Well, here I just draw the square, and then I cut it horizontally into 2 pieces. Cut it vertically into 2 pieces. So the first piece is the one on the left, second piece is the one on the right. And then we stretch horizontally by 2, and then contract vertically by 1/2. And stack the block on the left to the block above, and the block on the right to the block below. So now we have a map from this rectangle to itself. And if we want to turn this into a continuous map, we have to glue the sides of this rectangle. So glue the 4 sides of the rectangle. And the gluing is just going to be as illustrated in this picture. So basically, you see that all the horizontal sides can be decomposed into subintervals of length 1/2 to the n, if we consider the original thing as the unit rectangle. And all the horizontal intervals, as well as all the vertical intervals that of the same length, are glued together. So this is the gluing. Yeah, so the gluing pattern is all the horizontal sides get cut into those smaller pieces as shown in this slide, and those that have the same length get glued together. And vertically, is also those that have the same length get glued together. And now we see that the map get extended to this surface, but this surface has like not very good behavior at the ends. So you can see that basically the dotted lines at the 2 corners, around the 2 corners, we can think of this as the 2 ends of this surface. Well, actually, they become just a single end. Yeah, all the dotted lines just become a single end. And the topology around these dotted lines of the map around those dotted lines are going to be complicated, because it's basically, it's some kind of hyperbolic behavior. We are getting close in one direction and then moving away in another direction. So that's not good. So the idea is that we do this blow up process. So we just, instead of having the 2 corner points, we replace the corner points with a line. So and then just turn that small n into 2 infinite strip into like four infinite strips, and two of the strips get glued together, two other strips get glued together. Basically, that's the situation. Yeah. So this is the blow up process. So we try to make the small edges become longer and then have them go off to infinity. And at the corner points, we just add the lines. And also, to see this example, earlier I mentioned that once we get to an Endperiodic surface, we can consider the mapping torus, and then that will give us a free manifold with cylindrical ends, and then we can add some leaves at closed leaves at infinity, like add some boundary at infinity, and glue them along the boundary so that now we have a closed free manifold with depth one foliation. And we can perturb this free manifold with depth one foliation to get some foliation of the same free manifold over the circle. Well, once we do that, we get like a sequence of elements inside the first fiber core. So this whole construction is described, like basically the construction described in the paper by Landry-Minsky-Taylor. Well, in this particular example, if we carry out that process, the resulting finite surface maps, they are not going to be pseudo-Nosov anymore. But on the other hand, it has some pseudo-Nosov pieces. So the main pseudo-Nosov pieces of those surface, like closed surface maps, if we just write down the horizontal and vertical foliation, and then consider so that under those under the invariant measures in the horizontal and vertical foliation, we assign the surface half translation surface structure, and now the map is going to be an affine map on this translation surface. So if we consider that, then we can actually write down the translation surface structure, which of one of the perturbed version, so which is going to be look like this. Well, what's nice is that you can see that this can be seen as, in some sense, an approximation of this picture. So it's like instead of having the horizontal and vertical edges going off to infinity or coming from infinity, we let some of the vertical edges becoming horizontal. So if we allow that, then that kind of approximation, then we get this new flat surface structure. But I don't know how general this phenomena is, but like whether or not this is only like happening in some really special example. But of course, this is just a side remark. This phenomena is unrelated to the main point of our paper. Okay, so yeah, in the last some like 5 minutes or so, or I just mentioned some further questions. Firstly, the whole construction that we did is really constructive, so, like really explicit and algorithmic. So basically, everything can be computed very explicitly. So yeah, a question will be, can we just implement this algorithm and then have this as a Sage package or something like that, so that people can make use of it if they want to look at some examples of Endperiodic surfaces. And secondly, yeah, whether or not we can connect this argument with the calculation of time-order polynomial or varying polynomial of certain of the fiber cone, which is the one that's adjacent to the vector corresponding to these Endperiodic surfaces. I think this should be doable, because essentially, yeah, doing the varying is like just doing triangulation, changes in triangulations of these flat surfaces. And next, so this is another question. So for mapping classes over certain of surfaces of a given genus, there's a question of understanding like what's the smallest possible pseudo-Nosov stretch factor of a mapping class given the genus of the surface or the topological complexity of the surface, in the case where the surface is of finite type. In other words, either closed or a surface with finite many genus and finite many punctures. And we can, so in that case, there are some known results for low genus surfaces, and also there's some results on the asymptotics by Penner and other people. And there's a paper that I did with one of my collaborators, Marissa Lavin, a while ago, where we have the same, we also get analogous asymptotics for this minimal stretch factor for Endperiodic surfaces. So here the complexity, topological complexity will just be like the basically the genus of the core. And the question will be, well, if fixing the topological complexity of an Endperiodic surface, can we also calculate the minimal stretch factor for some special cases of low complexity infinite type surfaces? The reason that we can ask this question is that our construction basically also, the construction goes in two directions. So basically, once we start from this map from a collection of rectangles to themselves, they give us we can start from the collection of rectangles with this map and construct an Endperiodic Pseudo-Narsov mapping class. But on the other hand, if we start from an Endperiodic Pseudo-Narsov mapping class, we can get the Markov decomposition. So also get like a collection of these rectangles getting sent to themselves. So because this construction goes in both ways, it's potentially possible that we may be able to make use of this construction, and together with some more combinatorial techniques to get this minimal stretch factor, not just the asymptotics, but the actual number for cases where the topological complexity is low. And lastly, this is a more this is a question that's kind of less related to this paper. So in the Endperiodic mapping classes, for Endperiodic mapping classes, we can all these people have built such a nice theory where a lot of the results in finite mapping class groups can find analogies in this larger family. But if we go like beyond Endperiodic family, whether or not we can also have similar theories. So in particular, the question that I've been thinking about for a while is that if we consider, instead of having like H composed with G, like the deck transformation composed with G, if we consider like H, instead of a deck transformation, we can consider like the deck transformation composed with the lift of some self-map from S to S. So certain self-maps of S to S can be lifted to the Z-fold cover. So we consider that lift composed with G. So that's still another mapping class that can be written down using finite amount of information. But can we build an analogous version of the Handel-Miller theory for that mapping class? Well, that's like the question that I'll be interested in seeing more about. Yeah. Okay. So I think that's all I have prepared. So if you are interested in the details of our argument and our construction and also the algorithm, you can take a look at the paper. Yeah.
All right. Yeah. So let's thank our speaker, and let me start the discussion. So, are there comments or questions? Yeah, let me ask a basic question, right? I mean, the weak Perron numbers, I mean, where do they come from? They essentially come from Perron-Frobenius eigenvalues of your matrix.
Yeah, and potentially taking roots. Yeah.
Okay, I see. I see. So, are there other comments or questions?
Can I ask a question?
Yeah.
So what you said that you cannot realize these weak Perron numbers by finite type Riemann surfaces. Is it the theorem that you can't?
Yeah. Oh, sorry, I didn't hear.
So is it the theorem that you cannot realize some weak Perron number by a finite type Riemann surface?
That's correct. That's correct. Yeah. So because for finite
see.
type, we need to buy Perron. So it's a much more restrictive condition.
Oh, I see. So because finite type is biparallel, if a number is not biparallel, you cannot realize.
That's true. Yeah, yeah. And also in particular, like all the integers, they are weak Perron numbers, and they can be realized by infinite type, but they cannot be realized by finite type. Yeah.